Okay, so next one is to continue with the solution to differential equation. So differential equation, as you know, involves the differential or differentiated form of the equation. There's an independent and dependent variable. So how do we find the solution to the differential equation? Okay, so if you have a solution, an algebraic equation, okay, algebraic equation is just a simple equation, okay, x or y in terms of something else. So if you have this equation x plus 7 equals to 10, then you can find the solution to this equation as a number. So for example, you can solve x equals to 3. So the solution to this equation is x equals to 3, a number. Or if you have the polynomial equation of this, then you try to solve, and you can also have a set of real and complex numbers. Or you can also, if you solve two simultaneous equations, this and this, you can get a vector x and y equals to these values. So these are some solutions to algebraic equation. But how do we say something is a solution to differential equation? So the solution of differential equation is not the same as the case of an algebraic equation. The solution of a differential equation can be either a function. Okay, so for example, the solution for the differential equation d2x over dt squared plus 25x equals to 0 can be x equals to a sine 5t plus b cos 5t. So we will talk about how to get this solution in the next week's lecture. But yeah, just for now, for the time being, just accept the fact that the solution of this equation is this. And it could also be a family of function. For example, the solution of multiple differential equation, because in this case, dx dt and dy dt, so you have two dependent variables with one independent variable, so you must have two sets of equation. So you can have x in terms of t and y also in terms of t. So these are the solution for a family of ODE. Okay, so how do we find the solution of differential equation? Okay, so the solution of differential equation can be further divided into two types of solution. One is the general solution and B is the particular solution. So what are general and particular solution? So general solution is basically a function that will satisfy the differential equation and contains one or more arbitrary constants. So it's like when you do the integration. So whenever you are not given the limits of integration, so you will have to add a constant at the end. So something like that. So that is a general solution. Okay, so for example here, if you have the general solution of this differential equation, so dx dt equals to minus x, so you can solve to get x equals to a times exponential of minus 4t. So here, any arbitrary constant a can satisfy the equation. Okay, so a is sort of the constant of integration when you solve for this differential equation. Particular solution, on the other hand, gives you the particular numerical values to the constant in the general solution results. So how do you find the particular solutions? You can find the constants, the arbitrary constants, if you are given initial or boundary condition. Okay, so for example, so you know that for this particular equation, dx dt equals to, okay, dx dt equals to minus 4x. This one, you can get the solution x is equal to ae minus 4t. So you can get the value of a if you are given when t is equals to 0, then x equal to 2.5. So this is your condition. So x as a function of t is this. When t equals to 0, x is 2.5, then you can work out what is the value of a, and you can find out that a equals to 2.5. Thus, the particular solution is x equals to 2.5 times e to the minus 4t for this particular condition. Okay. General solution and particular solutions indicates that there are an infinite number of solutions to the differential equation unless we are given the specific condition of the problem. Okay, so practically it could be anything under the sun. The value of a in this example here just now could be any value, and but if you are given a specific condition, then only you can find out what is the particular value of A. So the actual solution to a differential equation is the specific solution that not only satisfy the differential equation, but also satisfy the given initial condition. So how do we obtain the particular solution? So we mentioned previously, and also in this slide also, you need to know the boundary value or the initial value. So we are given either the boundary value problem or initial value problem, so you can substitute that into your solution to get the constants. So yeah, let's compare what is boundary value problem and what is initial value problem. So okay, if you are given a boundary value problem, it means that the conditions are specified at different values of the independent variable, usually at the extreme points or boundaries of the system. So okay, let's say the solution of this particular differential equation, so d2x over dl squared plus 25x equals to 0. So the solution is, the general solution is, if you're not given any boundary condition, so the solution is x as a function of L equals to A sine 5L plus B sine cos 5L. So you don't know what the values of A and B, but if you are given the boundary condition, x value when L equals to 0 is 4, and when L equals to 10, x equals to 7, then you can work out the value of A and B, and you can get A equals to 5.78 and B equals to 4. So this gives you the particular solution given the boundary value problem. Okay, so initial value problem are when conditions are specified at the same value of the independent variable. Okay, for example, given the same differential equation, so you still have the same general solution like what you have here, but now the initial condition is given at L equals to 0. So when L equals to 0, x when L equals to 0 equals to 4, same like what you have here, but there's another condition at the same value of x, but now you are given the x prime, so it's the dx dl. So dx dl when L equals to 0 is equals to 8. So dx dl equals to 8 when L equals to 0. So in this case, you will get a different equation, different value of A and B constant because of the given initial condition. Okay. For first order differential equation, the condition can be treated as initial value or boundary condition. It doesn't really make a lot of difference, but for higher order differential equation, the distinction will become obvious. Okay. Right. So here is just a graphical representation of the boundary condition and the initial condition. So what difference does it make? Like okay, let's say your function just now is x as a function of L. So x is the displacement of the beam, and L is the length of the beam. So a cantilevered beam under the boundary condition. Okay, here if you want to know what is the vibration response that occurs under the boundary condition, when when L equal to 0, x is equal to 4. So at this point, L equals to 0. Then you displace the tip of the beam by 4 cm upward, and also you displace the middle of the beam, i.e. when L equals to 10, x equals to 7. So then you can get a function of x in terms of L, right, at different values of A and B. However, when you define the cantilevered beam using initial condition, i.e. when L equals to 0, you put the beam by 4 meters upward from the origin, and you impact the tip simultaneously to cause it to move with an initial velocity of 8 meters per second. So x prime is when L equal to 0 is equal to 8. So these are the different graphical representation of boundary condition versus initial condition for a cantilevered beam, just to help you illustrate what happens when you are given such condition. Okay. So next is verification of differential equation solution. So let's say you're given a solution to the differential equation. Okay, let me try to make some sense here. Why do we need to verify the differential equation solution? So just now, if you have just algebraic problem, so you know that the solution for x plus 7 equals to 0, you can solve for x, then you get x equals to 3. So how do you want to verify whether x equals to 3 is actually the solution to this equation? Is that you put the actual value of x now and plus 7, and then, oh, okay, it's equal to 10. So meaning the x equals to 3 is the solution to this equation. So yeah, in this case, because it's not obvious, how are we confident that the given function is a solution to that ODE? So we must verify if the function is indeed a solution for the given ODE. So the solution needs to be differentiable, meaning you can differentiate with respect to the independent variable, and must also satisfy the given equation. Okay, so there are two types of solution. One is explicit and one is implicit solution. So how do we define what is explicit and what is implicit? So it's easier to define the explicit solution and then tell you what an implicit solution, then that will give you what is implicit. Okay, what I mean is, let's define what is explicit solution, and whatever that is not explicit, then it is implicit. Okay, so an explicit solution, okay, this is the definition. An explicit solution is any solution that is given in the form of y as a function of the independent variable. So in other words, the only place that y actually shows up is once on the left side and only raised to the first power. So, okay, you must have y in terms of something, and it only appears left side here one time only and only to the first power. Okay, if you have a solution like y squared equals to q of any function of t, then this is not explicit. Okay, so an implicit solution is any solution that isn't in explicit form, meaning you have to imply what is y from the given function. Okay, so from y squared equals to something, then you need to find out what is y. So in order to find out what is y, you need to square root both sides to get what is y, right? So then only you will get, oops, what happened? Okay, maybe I'm too close to the end. So here you get y equals to plus minus the square root of the function q as a function of t. So here it is not explicit. Okay, this function here, y squared in terms of something, is not explicit. It is implicit because you have to imply what is the y. You have to still simplify the equation. Same as if you have cos of y equals to something something something, then that is still not explicit because then it is not just the y. You need to have just the y only. Okay, so y is cos apa nama ni? Yeah, something. It's whatever is on the right hand side there. So yeah, just to emphasize it again, explicit is when you have the dependent variable at the left hand side once only and only raised to the first power. Anything other than that is implicit solution. Okay. Let's do example 4. Find the implicit and explicit solution to the first order differential equation y dy dt equals to t. Okay, let's do this, and you're given the boundary condition y when t equals to 2, y equals to -1. Okay, so let's try to do this example. Okay, so here example 4. We are given y dy dt equals to t, and y when t equals to 2 equals to -1. Okay, not to be confused with this notation, it means that t equals to 2 and y equals to -1. Okay, So, all right, from this differential equation, this is a simple differential equation, so you can just separate the variables and then you can integrate both sides. Then you get y squared over 2 equals to t squared over 2. Don't forget the constant, you have c. So then you can put in the value of t equals to 2 and y equals to -1 inside this equation to get the value of c. So y equals to -1 squared over 2 equals to 2 plus c. Then you can solve for c. You get c equals to -3 over 2. Then from here you can write down y squared over 2 equal to t squared over 2 minus 3 over 2. Then you can just eliminate this over 2's. Then you get y squared equal to t squared minus 3. So this gives you an explicit solution because it's y squared instead of just y on the left hand side. So then what is the explicit solution for this? So you want y at the left hand side just once and raised to only the power of 1. Okay. So here you have plus minus t squared minus 3. So here you have two explicit solution, but which one is the what? Is the true explicit solution? So this is where we need to work on it. Okay, so you can write y1 is positive t squared minus 3 and y2 is negative t squared minus 3. So which one of these is one that is true? So then you can try putting in the boundary value problem or initial value problem. It doesn't really matter because this is first order. So you just put this value. So, okay, so for y1, if you put t equals to 2, then it should be -1, right? Okay, so this is what you want to satisfy. So if you put t equals to 2 into y1, so y1 you will get positive 2 squared minus 3, then you get positive. 4 minus 3 is 1, so positive 1. If you put into y2, t equals to 2, you get negative 2 squared minus 3, you have negative 1, so you get -1. So y2. So this is the one that satisfies the given condition. So then we say that y equals to negative square root of t squared minus 3 is the true explicit solution to the differential equation. This is still an explicit solution, but not true, not the true one, because it doesn't satisfy the given condition. Okay, it doesn't satisfy this one. So this is the true explicit solution. So what's next in the slide? Okay, so it says that check which one is the true solution by applying the boundary value problem. So now we know. So we know that y2 with negative square root of the solution is the true explicit solution. So next we want to verify the solution. So here, to verify that the y squared equals to t squared minus 3 is the implicit solution, so we need to deduce the differential equation from it. Okay, so what it's saying is that, okay, fine, now you say that y squared equals to t squared minus 3 is a solution for y dy dt equals to t. Right, so you say that this is the solution for this differential equation. Prove it. So what we do here is we need to derive or deduce a differential equation from this given explicit solution. So yeah, let's do that. So then we need to differentiate both sides with respect to t. So d dt of y squared equal to d dt of t squared minus 3. Then yeah, you differentiate that to y, then differentiate dy dt and equals to to t only. And then you eliminate the 2, then you end up with y dy dt equals to t. Then you have proven that this y squared equals to t squared minus 3 is the the implicit solution to the given differential equation. So problem solved for one thing. Next is you want to verify that y2. So now you want to verify that y2 equals to negative t squared minus 3 is the true, the explicit solution for y dy dt equals to t. So from here, you want to get to here. How? So you do the same thing, okay? So just differentiate left side and right hand side. Okay, so yeah, so we want to do that. So just put y to not confuse us with the 2 and stuff. So d dt of y equal to d dt of negative square root of t squared minus 3. So dy dt equals to d dt, I mean, whenever there involves a square root, I prefer to put it as power of 1 over 2. Okay, so d dt minus, wait, not yet. Okay, negative 1 over 2 t squared minus 3, negative 1 over 2, and also differentiate the inside, you get 2t. So then you can eliminate these 2. So you get negative t over, because it's negative half there, so you put it down here. Okay, so you get dy dt is equal to negative t over square root of t over 3. I mean t squared minus 3, sorry. And then what's next? Next is we substitute this derivative into the left hand side, because the left hand side of the differential equation is y dy dt, right? So because we want to prove that this is the solution for this y dy dt equals to t. So we want to prove that when we put this dy dt into here, we get t. Okay, so then we put y times dy dt is negative t over square root of t squared minus 3, and our original y is negative square root of 3 squared minus 3 times the negative. Okay, so you can see that you can eliminate these terms, and negative becomes positive, so you just have t. So you have proven that y dy dt, you get t when you substitute this explicit solution inside here. So you have verified, okay, basically you have verified the solution to be the solution of this given differential equation. Okay, so next is to try to prove that y1 plus t squared minus 3, the whole thing square root, is also the explicit solution for the differential equation. So you can follow the same process. You will end up with y dy dt equals to t. Okay, just follow the whole thing here, but you do it yourself. Now that you've seen how I do it, and actually it's already available in your notes. So why don't you try the same process, but this time you have y1 equals to plus square root of t squared minus 3, and try to see if you end up with y dy dt equals to t. So you can see that actually y1 equals to plus square root of t squared minus 3 is also the explicit solution for the differential equation. So both are actually explicit solution to the differential equation. Only in this case, when you want to satisfy this boundary or initial value, that this particular equation is the true explicit solution for the given ODE. Okay. All right, so before we proceed to the next part of the video, let's do this example 5. So this is also available in your notes. So for the differential equation, yeah, this one, can read it on your own. Given the initial condition, you suspect that y squared times exponential of 3xy minus x equal to 1 is the implicit solution to the differential equation. You suspect, or you were made to suspect, that this is the solution. But anyway, please verify the solution. Please verify whether this solution is indeed the solution to the differential equation given the initial condition. So what you do is, yeah, you can look at your notes and follow the steps, but yeah, let us just try to do it together. Okay. So you can rewrite the equation. So 3y cubed e 3xy minus 1 plus 2y times e 3xy plus 3xy squared e 3xy times dy dx equals to 0. So don't be intimidated with this. Just they're to confuse you, I guess, but I'm sure you're not confused. So the condition you're given is when x equals to 0, y equals to 1. Okay. Yeah. So I think wait. Okay. And the solution you are given that you want to verify is this: y squared times e 3xy minus x equal to 1. So verify that this equation is a solution for the above differential equation. Okay. So then, starting with that, we differentiate with respect to x. Okay. So differentiate with respect to x, y squared and differentiate with respect to x dx, and differentiate with respect to x dy. So here you need to recall the differentiation of the product rule, and u dv dx plus v du dx, right? Okay, so that I think you can do that. Then you can take out the, yeah, y plus you have to differentiate the exponential, and then dx is 1, d1 dx is 0. Okay. Yeah, just collect everything. Y dx plus, so when you differentiate 3xy, this is also another uv term. So d dx 3x times y plus 3x times dy dx. So this is this part. Okay. So you differentiate 3x, you get 3. Then times y plus 3x dy dx minus 1 equals to 0. So you can put this y squared inside. Okay. Three y cubed plus 3xy squared dy dx minus 1 equals to 0. So what you do is you just collect all the similar terms and factorize, and you can prove that this is the solution of the given ODE. So let's do that. So you can get 3y cubed e 3xy, because you just now you're just expanding, and then minus 1 because it's got nothing to do with the dy dx, and then you factorize the dy dx, and then you get 2y e 3xy plus 3xy times 3xy 2 equals to 0. So this is actually the same with what you have in the original term here. So then you have now proven that this given function is indeed a solution for the given ODE. Okay, so you just deduce an ODE from the given solution. Okay, so let's move on to the next video.